do this. Okay, so here's an example I found that somebody had already typed up online. But it's a really good one. I actually Googled postal rates. Because if we look at this, if we were to go to the post office and we were paying for a large envelope that we wanted to mail, every time they put it on that little machine and weigh it. Have any of you ever been to the post office?
Yes.
Sure.
I love it. It smells good.
It does.
Doesn't it smell good?
Okay. All right.
Okay.
Well, they do have a graduated scale for how they charge us. Now, it says here that it's weight not over 1 ounce. So when we're mailing a letter, if it's between 0 and 1, up to 1, we would be charged this amount. But if it weighed 1.2 ounces, that would move us up to 2. And then let's say it weighed 2.05, what would that do? That would move us up to the 3. Okay, so if we were trying to graph this data, what would that look like?
Pretty jumpy.
It would look like stairs. It sure would. It would look exactly like stairs. So, I'm going to try to graph this. I have weight on this axis, price on the vertical axis, so this is my independent, my dependent variable. Weight not over 1 ounce. So somewhere between 0 and 1. Could my envelope weigh 0? No. So would it be a closed or open circle? Open. And we know from that to 1 ounce, it's going to be $1.22. So I need an open circle right here, and everything in this weight range would cost the same amount. Does it include 1 ounce? Yes. So open or closed? Closed. Okay. Then what happens at 1 ounce? Anything over 1 ounce but under 2 would jump up to $1.39. So not at 1, because at 1 it's this one, but all the way up to 2, it would look like that.
Well, there's really not stairs because there's no.
And then what would happen? This would go up to 156. So an open over to a closed. And then this would go up to 173. So we're almost right here. It's really close. They're slightly under. I tried to put it slightly under. Okay, and you see what this looks like. What does it look like? It looks like stairs. Okay. What this is what we'll refer to it as a step function, because it looks like stairs or steps. And so anything that a company would either round up or round down, we can display graphically using a step function. Can you think of something else, maybe besides postal rates, that this would happen with?
Number of people. So you can't like have a person. So you have to jump up.
We would jump up, but we wouldn't have anything in between here.
That is true.
Yes.
Taxes?
Taxes.
Gas prices.
Gas prices.
Wait, I thought gas prices were
It's supposed to be like
set
there.
because you can have part of the gallon.
But you wouldn't pay.
But they always rounded up to the nearest cent. Yeah. Okay.
Isn't it when you pay, like TCDY, that you pay per ounce? Or something like that?
That one may be more graduated.
That one's, yeah, because you can have part of it now.
Have any of you ever been to Atlanta and parked in a parking lot where they charge you?
At a meter.
And if you get to anything over 2 hours, they charge you the 3 hour and anything. So that's another one. So there are a lot of things that actually are modeled by step functions. Okay, so these have a lot of different names. We can call them step functions. They're also sometimes referred to as greater integer functions. We have 2 types. Sometimes we're going to round down, and sometimes we're going to round up. The rounding down has 2 different symbols here that we could use. The double brackets, or that kind of L's where it looks like it's bottomed out. the rounding down function can be called the floor versus the rounding up. See how the brackets just have the top part here? The up would be considered a ceiling function, floor ceiling. Alright, so what does this x inside these brackets, a rounding down, what does that mean? It means what we're going to do is we're going to convert any real number x into the greatest integer that is less than or equal to x. What is the greatest integer that is less than or equal to x? So I have a few here that we can look at. Okay. The first one, we have 2.3. Now, this is rounding down, isn't it?
It is.
So what is the greatest integer that is less than 2.3? 2. So that would round down to 2. Okay? The greatest integer that is less than 0.5. 0. The greatest integer that is less than negative 1.2.
-2.
Negative 2. The greatest integer that is less than pi. 3. The greatest integer that is less than negative e. Negative 3.
Why are we rounding down?
Oh, because all these say round down. What if they said round up? Let's go back to the first one.
How do you know if they're saying round? Oh.
Okay, we have 2 that mean rounding down. We have the brackets, and then the floor looking, and then we have
Very
the ceiling
confusing.
ones that mean rounding up. So this would be rounding up. What would this round to? 3. When we graph them, when we're rounding down, we round everything down, and it looks like this kind of step. What do you think this one would look like?
It's off.
The other way. We round everything up. And it would look like that kind of step. Okay, so let's take a look at our parent graph for our step function. So here we go. Here's our function, and I'm going to just pick some things. Let's do -1. What is the greatest integer that is less than or equal to -1?
-1.
-1. Okay, let's do -0.8. What is the greatest integer that is less than or equal to -1? Let's do -0.5.
-1.
Okay, -0.1.
-1.
0.
0.
Alright. 0.2.
0.
0. 0.75. 0. 0.99. 0. 1.
1.
What? 1.1.
1.
What?
So if
Okay,
it's like a,
so let's,
you can't bring it down. If it's exact, you can't.
right. So all of these things between -1 all the way up to 0 have a y value of -1. So everything between -1 all the way up to 0 have a y value. The value of the function is -1. Does that make sense? Every x value I plug in between here and here, will round down to -1. Now, every x value between 0 and up to 1, but not including 1, will round down to 0. And it looks like this. And then from 1 to 2, it's going to look like this. And then, do you see the pattern?
I see it.
Step, 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 nothing? Okay. Let's talk about the domain of this function. Were there any restrictions on things I plugged in over here? No. We can plug in any real number. So what would the domain be?
Negative infinity to positive.
Negative infinity to positive infinity. Now let's think about our output of this function, the range. What kinds of numbers am I getting out every time? Integers. It is the set of integers. And we do have a symbol for that. It's the double I. Looks like, I'll put it in a circle. Kind of looks like a double I, Roman numeral 2 almost. It really does the way I did it. The second one's not attached.
So it's
Wait, so the second little line, it's just like the one Roman
It's kind of
numeral
like,
with the little
you know, in English you do the double P for paragraph.
yeah.
That's kind of when we do the double R for real numbers. You do the double I
integers.
for integers. Maybe it's the second one that is attached. Anyway, if you did this, I'd know what you meant.
So if we just put a Roman numeral 2.
Set of integers.
How do you do it?
All right. So now that we know what the parent graph looks like, it's going to be a piece of cake to shift this one around. Here we go. Where will I place the first step in this step function?
At the point 3, 1.
3, 1. Okay. So at 3, 1, open, closed. What do I start with?
Say
Close.
Let's say close.
And I go over to open. And I jump up 1. Closed, over to open. Closed, over to open. Backwards. Closed, over to open.
Whoa.
Closed, over to open. Closed, over to open. Closed, over to open. Okay. What's the domain of this one?
Negative positive infinity.
What's the range of this one?
Double
Double I.
Somewhat double-eyed looking weird thing.
That's terrible.
Thanks.
I'm not good at that. Maybe I should just write the set of integers.
Set of integers.
Okay.
We wrote set of
Is this
integers.
the only function that correctly gives this graph that we could use to model this graph?
No.
None.
No.
Okay, Brian, you got another one. I'm ready.
No, I don't.
Yes, you do.
Look at that.
Who's got another one for me? All right, Tardy.
Y equals bracket x bracket -2.
Beautiful. So he had to start right here. Gives the same
Oh.
graph, doesn't it? Who's got another one?
Silly me.
You got one now, Brian?
Yeah.
Yeah, I'm ready.
Okay, bracket.
Okay.
X minus 4.
Okay, so
Plus
you're plus 2. Beautiful. Okay. So we could have multiple equations that actually give us this exact same step function. Okay. So what happens if I throw a negative out in front of this step function?
Is there a real world application for that?
And instead of going upstairs, we'll be going downstairs. So we're going to go here to here, and instead of going upstairs, this says go downstairs. Because it's a reflection over that x-axis, so instead of going up, it's reflected down here. Okay? Domain and range are all the same, aren't they? We still have negative infinity, positive infinity. We still have a range of the set of integers. Okay. What would this do?
It would
What?
stretch it.
Yes, it's vertically stretching it. So instead of jumping up 1 step,
We jump up 2.
we jump up 2. So the first step is going to start here at 1, and we're going to jump up by 2. Jump up by 2.
Oh, the range is going to
Jump down by 2.
That's all I got.
Ooh,
double I
good. So you've already discovered an issue with the range. So what is the range
Odd integers.
All
of the
integers.
set of odd integers?
I
Good.
agree with that. I can
So you put I though.
Odd. I.
And if it started like, if it was +2, then it'd just be set of even integers.
Yes, it would.
It's
Now, the other way we could do it is just by giving the pattern, like we could just say -3, -1, 1, 3, ... Now, sometimes giving the pattern is the only thing we could do, because what if this were a 3 here?
Without that.
Then, and this were a +2. Then our range would be 2, 5, 8, 11. We just have to show the pattern. Okay?
Couldn't we write like a function to show the pattern?
No.
We generally don't describe the range with a function, because the range is the output of a function.
Function.
Okay, how would this change if, whoops, I erased the wrong one.
Oh, no.
If it looked like that, what would that do to this?
It
The
would-
circles and
It
the
just
dots.
flip them, wouldn't it? So it would be open, closed. Oh, let's make sure. Let's think about that and make sure that's exactly what happens.
You know, it would shift up one and then do that, right?
Wow.
'Cause it's
I don't really know what.
It's ceiling. So let's think about it. If this rounded everything, if we plugged in 0.5, that would round it up to
1.
1, and 1 times 2 is
2.
2, plus 1 is 3. So
Five.
it would jump it up to here, wouldn't it? So it would shift it up, because it's going to round all that up. And then we go up by 2.
So would it shift up 1 or 2?
1.
So really all you should do.
And it would look like that. Okay, so with the ceiling ones, you have to think a little bit more about what's going on. It does switch it, the open and close, but it also is going to change where we start. Okay, you have a worksheet to do for homework. So if you're listening to this, I'll try to post the worksheets on my website for you guys from yesterday and today also.